Okay, so we've previously looked at adding and subtracting vectors. We did a little bit of work with multiplying a vector by a scalar value. Yeah, scalar value, in case anybody doesn't, or for anybody who doesn't remember, is we're looking at something like this. This is my vector, and I'm multiplying it by a scalar, meaning any any value that does not have a direction associated with it. So if this is my vector A, and I'm looking for 3A, I'm essentially just saying the number 3 times this, and of course what I'll end up with is the exact same vector tripled or made 3 times larger. Okay, so essentially that's the result of multiplying by the scalar value 3. So just in case you forgot again, scalar is just anything that is not a vector, meaning no direction. And again, that's going to be a pretty obvious thing. If we're not talking about changing the direction in any way, we're tripling it, we're multiplying by half, we're just going to basically take the existing vector and extend it or shrink it as appropriate. Flip it around if it's a negative. Sorry, before I go on, just want to quickly mention, I'm calling this the dot product. Essentially, we will be working with something that looks like this. I guess use fine, although I meant to put something else. Dot product is a certain type of multiplication. We later on will deal with cross product, where we use the more standard multiplication symbol. The two are very different things, and so we must be writing our work today with the dot. So first, an example of where this kind of comes up. Now, before we sort of get to the question, why would I ever do this, or where would this ever come up? How could I ever multiply a vector by a vector if both have some sort of direction and the direction isn't the same? It doesn't make a lot of sense. So an example from physics, again, if you haven't taken physics, no big deal. Just sort of trust me a little bit here that the formula to calculate work done on something is the force times the displacement. Okay, so if I'm going to push a box, or in this case, let's say pull a box with this brown rope, the box is going to slide across the floor, and the amount of work I do on the box depends on the force exerted on the box and the distance that I change it. I think it should be pretty clear that if I move a box 1 meter, I'm going to do less, it's going to require less work from me than if I'm going to move that same box 10 meters. Okay, so sort of the displacement matters in this case. How far do I actually slide the box? So if we just sort of look at this, and forgetting about the fact that we haven't seen the formula before, just if we trust that that's what it is, I'm interested in knowing, let's say if I move this box a distance of, let's say 20 meters, how much work do I actually do on the box? Well, first thing to recognize is if I'm pulling at this angle of 30 degrees, all of my force is not being exerted on the box, or at least not in the direction of the displacement. Some of my work is going this way, and some of the work I'm doing is going this way. The work that's going vertically is completely useless. Ideally, if I could exert the 50 units straight across, I'd be putting maximum effort into moving this box. By the same token, if I tried changing this and pulling this way, the box probably wouldn't even move, even though I'm exerting the same amount of force. So really what I'm interested in is the force in the direction of the movement. How would we figure that out? Well, without even sort of thinking too much, I recognize that this is, sort of if I put that back in, I end up with a right angle triangle here. The amount of the 50 newtons that is in this direction is going to be a simple trig question. So this is my opposite, this is my adjacent, and so the value of the adjacent will be, or sorry, if I look at this as cosine of the 30 will be equal to my adjacent divided by my 50. And so if I multiply 50 times cosine of that angle, I can figure out the amount of force in that direction. And that is about 43.3. So 43.3. Now, if the question is asking me for how much work did I actually do, well, I did 43.3 newtons worth of work in that, I applied 43.3 newtons of force times a displacement of 20. And so what's that? 866 Newton meters, or 866 joules. Okay. Now again, the units don't really matter to me. Newton meters makes sense. I'm applying newtons of force times meters. It happens to be the same thing as joules. But again, what's important is to recognize I have a force in a direction, a displacement in a direction, and what I end up with is a multiplication that results in some value. Now, the interesting thing here, or what I think should be the interesting thing here, is that the 866 joules is the amount of work I did. If I think about, if I've moved this box all the way over here, and then I've moved the box, if I move the box all the way back, there's sort of two possibilities. I've done 866 joules worth of work twice, meaning I would have a total, let's say, okay, if we move the box back, oops, box back, there's essentially two possibilities. One is that we did 866 plus 866, which is what, 1732 joules worth of work. The other possibility is we did 866 in one direction minus 866 because of the opposite direction, and that I did a total of no work. So the question would be, if I asked you to move a box halfway across the room, and then asked you to move it all the way back, and I said to you, well, you didn't do any work today, I'm not going to pay you, do you think that's fair? My suspicion is you don't. And so what that means is this is the amount of work I did, which means that these values here, very important, have no direction. Which means at this point, when I do a dot product, I'm multiplying two vectors, but I'm getting a scalar value. There's a number at the end that represents the answer, or that is the answer, but it is not in a specific direction. So, looking at a pure math problem now, if I have these two vectors, it asks me to find the A dot B. Given what we just saw, if I've got, I can sort of start with my two vectors here. Now here, recognize the direction of my displacement was across, the direction of my force was kind of up and to the right. And so the two vectors were essentially starting tail to tail, and then I was interested in the angle between them. Same sort of thing here now, two vectors tail to tail, and let's pick a nice number here. Let's go with 60 degrees because it allows me to do, oh, it seems like I'm frozen. Okay, so we'll pick a nice number here. I'm going to go 60 degrees between. I think it looks about right. And so based on what we saw last time, we need to deal with the cosine of our angle. So essentially, the dot product here, A dot B, is going to be the size of the vectors. Again, that's how we started here. We had a 50 Newton vector. We had a 20 Newton vector that was going to come into play momentarily. So we've got the size of A. We're going to multiply by the size of B. And we're going to multiply by the cosine of the angle between. And so we have 13, I guess, yeah, A is my blue, Again, it doesn't matter too much, but might as well be consistent here. B is my red, and cosine of 60 is the angle between. So recognize I'm doing the same thing as I did last time. I'm taking cosine of the one to get it into the orientation of the other one. So it would be like I extended a right angle up right here, and then I found cosine of the 30. The fact that I'm doing it out of order doesn't matter because, of course, I'm just multiplying three numbers. And as we've mentioned probably numerous times, 3 times 4 times 5 is going to be, can be done in any order. 12 times 5 is 60, 15 times 4 is 60, 20 times 3 is 60. I guess that's all the possibilities. So the order here doesn't matter. I'm going to multiply 3 times 4 times, this turns out to be 1/2. And so I now have, okay, 3 times 2, which is 26. So A dot B, again, is 26. And recognizing, again, just reminding us that that is just a number. It is not a vector of itself in itself. Now, if we look at the Cartesian vectors, there's have to be a way to work with those as well. One possibility, of course, is to just kind of go through the work. If we have A dot B is this formula, which is essentially what we just developed on the last page, I can find the size of A, I can find the size of B, and I can multiply by the angle between them. Now, hopefully we all recognize that if I have vector 3, 4, this is a 3, 4, and then it turns out that a 5, if you don't know that, that's fine, but that's Pythagorean, a fairly popular Pythagorean triangle. 3 to one direction, 4 the other direction, square the 3 is 9, square the 4 is 16, add them together is 25, square rooted is 5. So I've got the 5 from A times the 6 and 8 is another Pythagorean triangle that gives me a size of 10, and I want to multiply by cosine of the angle between them. I get a little bit hung up at this point because I don't know the angle between them, but if I look at the Cartesian plane, I can probably come up with one. So I'm looking at 3, 4, so 3, 1, 2, 3, 4. That is my first vector. And that is the, I guess it doesn't really matter, I'll make it red. The second vector was 6, 8. So I go out 1, 2, 3, 4, 5, 6, and up 8. It's 1, 2, 3, 4, 5, 6, 7, 8 to get my second vector. And lo and behold, rats. The second vector ends up being exactly on top of the first. Okay, so nice example to choose. That means that the angle between them, I guess, is just 0. And if we multiply this out, we have 5 times 10 times 1. Cos of 0 is 1, which is 50. Which again, probably makes sense to us. If we're talking about multiplying a vector that's size 5 times a vector that's size 10, and they're actually in the same direction, getting an answer of 50 makes perfect sense. So that works out pretty nicely for me. That said, if the angle had been anything other than 0, it would have been pretty crappy for me to try to figure that out. Pretty difficult. Darn, I should not have said that. It would have been pretty difficult for me to try to figure that out. Turns out, though, that if I just kind of look at the numbers here, I have a 3 and a 6 in the horizontal direction. I have a 4 and an 8 in the vertical direction. So I have a 3 and a 6. I have a 4 and an 8. I'm doing multiplication. Well, if I'm looking at these numbers carefully, I might be able to recognize that that is 18, that is 32, and that those two values together add up to 50. So it turns out that there's another way to find the dot product when we have a Cartesian vectors. And it actually works out to be quite easy, quite nice. And it is, although this may not look quite easy, quite nice, it is, oops, I have 2 copies of it there. and have extra copies of this too. In order to find the dot product, if I'm given the Cartesian values, I can simply multiply the first coordinate, if you will, the x value, if you will, from each vector, multiply the y values, or the horizontal components and the vertical components, and then add them together to get our final answer. And I think I'm going to stop there. So essentially what you need moving forward, this formula right here will be quite valuable and necessary to know and use, as will this one down here. Hopefully a little bit of understanding came from the video, and you're not just going to be thinking, well, I have 2 new formulas to memorize and that's why I do it. There are practical applications for them. We'll run into them throughout the next few sections, the next few days, let's say. But this is the pure math of how it all works out.